All right, greetings everyone. Welcome back to another fantastic video for learning calculus. Today we can be continuing on with section 2.2, building on what we learned about limits in our first video on 2.2. So let's get into it. So first we're going to remind ourselves of the definition of a limit that we left off with at the end of the first video. So we say that the limit as x approaches a of f of x equals this value L, if and only if the limit as x approaches a from the left-hand side, remember that's what this negative sign here means, is that we're approaching the value from the left-hand side. So the limit as x approaches a from the left-hand side of f of x equals L, and the limit as x approaches a from the right-hand side of f of x also equals L. So if we have both of those things, then we know that the limit itself over here on the left, that this one exists. Okay, and remember this if and only if thing. Okay, that tells us that if one side of the if and only if is true, then the other side is true. So knowing these two things on the right together tells us that the thing on the left here is true. But also because it's if and only if the thing over here on the left is true, then we also know the thing on the right is true. Okay, so that's how an if and only if works. All right, so let's look at finding limits in a way a little bit different than we did on the last video. So here we're going to be dealing with this function f of x that's given by sine of pi times x over x minus 1. And the first thing I want us to think about is the value x equals 1. Is this value here in the domain of this function? How do we figure that out? Well, one way to check is to plug the value in. So to go here and evaluate at f of 1, and I'm going to do it a little further over here. So f of 1. Okay, and if we do that, what we're looking at is sine of pi times 1, plugging in the 1 for x on the top, over 1 minus 1. And hopefully you see we run into a problem here, right? Down in the denominator, we'd have 1 minus 1, which would give us 0. And we know we cannot divide by 0. And so that's a problem, right? So that tells us that 1 is not in the domain of this function. All right, so now keeping that in mind, however, we still are interested in looking at what the limit as x approaches 1 of this function f of x would be. Okay, so let's look at how we would do that here. Now, one thing you might be thinking that we could check out is the graph of this function. So let's go ahead and do that. So I'm going to pull up my calculator here. Okay, and I'm going to go ahead and graph this function. So I'm going to go into my y equals here, put in the function. I'm going to be very careful about how I do parentheses here. So I'll do sine of pi times x divided by, I'm going to put that whole thing in the denominator in parentheses because I want to divide by that whole thing there. Okay, we'll get that. And if you're doing this along at home, you also want to double check that your calculator is in radians mode, which it looks like mine is, so I'm good to go there. I'm going to graph this. So we get something that looks like this, and we're looking at the limit, remember, as x approaches 1 here. So what I might do in my calculator is hit trace. I'm going to trace along that graph, watching as my values of x get closer and closer to 1, which you can watch that here in this box that tells us what values we're getting closer and closer to. So as we get closer and closer to 1 there, it looks like the outputs are getting closer and closer to negative 3 point something. There's a negative 3.12 maybe. Go back to the left, negative 3.1 something. Kind of hard to tell. So we could also zoom in. So press zoom 2 and zoom in there. Get a little bit better picture. And try to trace now. And let's see, looks like a negative 3.12, maybe a negative 3.14, negative 3.139. Kind of hard to tell exactly what that value is that we're getting closer and closer to. And also note, again, 1 is not in the domain, so we can't just plug in 1 into the function to see what we get as the output. That won't work for us. So what are we going to do instead? So what we're going to do is use a table of values, and that's what this, when you see this term estimating numerically, this is what we're talking about, is what we're about to do. So using a table. So notice here I have a table with inputs and outputs for my function. Right now I just have the inputs. We're going to fill in the outputs. But notice when you look at the values that I've chosen, I start here at an input value of 0.5, and then I increase the input values, and they get closer and closer to 1 there. Again, we cannot input 1 into the function. We can get really, really close to 1. And then we can also come from the other direction and approach 1 from above. So we're looking at the values as they approach 1 from below and the values as they approach from above. And so what I can do is take these values individually, plug them into the function, and see what I get each time. So I'm going to do that with the first one. So I'm going to use 0.5, so I'm going to use my calculator here. Go ahead and clear my drawings out. So I'm going to do sine of pi times the first thing, which is 0.5, divided by, again, very carefully using parentheses, do 0.5 minus 1. And when we do that, we end up with an output of negative 2 there. So in this table here, we could say that our output when we input 0.5 is negative 2. All right, and we'll continue on with these other values. Now, as you can imagine, there's going to be a lot of clicking here, right, on your calculators, because then I have to go through and do sine of pi times 0.9, and divide by 0.9 minus 1. And in this case, we end up with negative 3.0902. I'm going to use several decimal places here. But before I write that down, just notice this is getting to be a little tedious, right? Having to put in this whole thing every single time. So to avoid that tediousness, we're going to use some of the nice, some of the nice features of our calculator. So the next value I have to put in is 0.99. So rather than write out that whole equation again, plugging in 0.99, what I'm instead going to do is input 0.99, use this little STO button in the corner here, which is going to put that arrow in, and then I can hit the X button. And when I press enter, what my calculator is going to do is store the value of 0.99 for X. And then I can do sine of second pi times X divided by X minus 1. And what the calculator will do is it will evaluate this formula using 0.99 as X. So we do that. In this case, we get negative 3.141, looks like 0.8 or negative 3.1411. And then when I go to do the next value, which is 0.999, I can store that as X. And now, rather than have to plug in this whole formula again, if I press second enter, and then press second enter again, what this does is it makes the calculator go back to other things I've typed in before. And notice it's brought up this sine of pi x divided by x minus 1 thing again. And if I press enter, now it's evaluated the function using the value x is 0.999. Okay, so that's one way to save yourself some time when you are having to plug in a lot of these things. All right, so going back to our table here, I have already calculated several of these values or all of these values, so I'm just going to fill them in. So this one here, when we just saw when we input negative, or excuse me, when we input 0.9, we get negative 3.0902. We input 0.99, we get negative 3.14108. And when we input 0.999, we get negative 3.14159. Okay, so those are values approaching 1 from below. Let's also look at the values approaching from above. So I'm actually going to start down at the bottom there at the 1.5. So if I input that, I get negative 2 as my output. When I input 1.1, I get negative 3.09017. And then 1.01 is going to give me negative 3.14108. And then for 1.001, we get negative 3.14159. And just to remind ourselves, what we're trying to figure out here is what is the limit as x approaches 1 of f of x. Now thinking back to that limit definition we had at the very beginning of this video, that limit only exists if the limits from the left-hand side and the right-hand side are the same. So if we take a look at what we've got in our tables here, as we approach from this direction, so starting at 0.5 and going to 0.999, and then as we approach from the other direction, are we getting the same thing? Well, the values in each case seem to be converging towards this value negative 3.14159 on both sides. We definitely see that it's converging towards the negative 3.14, and as we get finer, that negative 3.14159. Does that value look familiar? Negative 3.14159. Oh yeah, that's what pi is, right? Now this one just so happened to work out nicely like that. Often these will just be negative answers, but in this number here, or sorry, often they will usually be decimal answers. But this one here came out very nicely, and actually turns out that the limit there we get is negative pi, or negative 3.14159, and all the decimals that come after that. Pretty cool, huh? All right. So that is estimating limits numerically. Again, we created a table with values that are approaching the number that we're approaching in our limits. So in this case, we were looking at values approaching 1. Okay, and we look from both sides. So we have to look as we approach from the left-hand side, or from below, as well as the right-hand side, which is above. Okay, the next thing I have on here is an estimating limits numerically example, another one where we're asked to estimate the limit as t goes to 0 of 5 to the tth power minus 1 over t. This is one that you will do as part of your classwork assignment for section 2.2. It can be done very similarly to the one we just did, and so you can work on that yourself and let me know if you have any questions. All right, let's look at another possibility for limits. So here we have the function f of x equals 1 over x minus 2, and we're not going to look at our calculators for this one. We're just going to do this numerically. So the first thing we're asked to do there is to estimate the value of the limit as we approach from the left-hand side. And then after that, what happens is we approach from the right-hand side. And so I've already set up the tables for this one. So let's take a look at this. And again, before I show the tables, we want to pick values approaching, getting closer and closer to 2 from below for the first one, and values approaching 2, getting closer and closer from above. And so you'll notice, if I do that, this is what we end up with. So for approaching from below, that's that first table there. So I'm going to label that with a 1. So that is this table here on the left. Okay. And notice we have 1, we input 1, we get negative 1, 1.5, we get negative 2, 1.9, negative 10, 1.99, negative 100, 1.999, we get negative 1,000. So it looks like the values there are getting more and more negative. And we probably assume that if we continue plugging in values that are closer and closer to 2, we we would get that same thing. So it looks like here the limit is approaching negative infinity because the values are getting more and more negative. Okay. However, if we look at the second table now, so I'm going to label this one as number 2. Notice that we input 3 and we get a value of 1. Input 2.5, we get a value of 2. 2.1, we get a value of 10. 2.01, we get a value of 100. 2.001, we're getting a value of 1,000. And it appears that as we get closer and closer to 2, these values are getting bigger and bigger, which looks like it's approaching positive infinity in this case. So notice when we approach on the left-hand side, we get closer and closer to negative infinity. Approaching from the right-hand side, we're getting closer and closer to positive infinity. And again, keeping in mind our definition that in order for the limit to exist, it has to be the same on both sides. Think about this. What does that tell us about the limit as t approaches 2 of f of t? You guys are right. That means that it does not exist. Okay, because those two limits from each side were different. Now, let's go back to our calculator here and take a look at what is going on with the graph of this function. So, clear this stuff out here. Go back to my graph. I'm going to input this function. So 1 divided by x minus 2. And I'm going to put my zoom back to standard. So I'm going to do zoom 6 so I get a standard. And you'll notice if we take a look at the graph here, as we approach from the left-hand side, we see again the graph going down. Approaching from the right-hand side, we see again the graph going up, which matches our findings that when we approach from the left-hand side, we go towards negative infinity. From the right-hand side, it approaches positive infinity. And in fact, hopefully this looks really familiar. If I clear this out again. And you recognize that this is a rational function. And what is happening right there at the value of 2? Right, we have a vertical asymptote there. Okay, and this is one of those vertical asymptotes where the tails are going in opposite directions. And so we see that in this case, we cannot say the limit exists because, again, on each side we are approaching, even though they're both going towards an infinity, they're going towards different infinities. So we can't say that the limit exists there. Now, let's look at some other options, though, when we're talking about rational functions. So this first one here on the left, okay, so that's what we were just talking about. So we see here that the tails are going in opposite directions, so there the limit would not exist. But on this second one here, notice that from the left, the output values go towards positive infinity. And on the right, they also go towards positive infinity. So this would be an example of where our limit would exist because from each side, they're approaching the same thing. And we see a similar thing here in the third one. As we approach from the left, we're going towards negative infinity. From the right, also towards negative infinity. So therefore, we know this would be another one where the limit exists because it's getting closer and closer to the same thing from both sides. All right, so one last one. We're going to look at the limit as x goes to 0 of the sine of pi over x. And I forgot to point this out in the last one. But notice again, in this one, very similar to the first one we did, the value we're approaching, 0, is not in the domain of this function. And we know that because if we look inside of our sine function here, there's an x in the denominator. And we know that if we plugged in 0 for x, that would cause us to divide by 0, which we know is not allowed. Okay? So we definitely cannot find the limit that way. So what are we going to do instead? Well, like it says, we'll do numerically. So we'll have to set up this table with these values approaching 0 from both the left-hand and the right-hand side. And check out what happens when we do that. Well, in that first table there on the left, when I approach from the left-hand side. So I start at -1, go through -0.5, -0.1, -0.01, -0.001. I see that for my output, I'm getting 0 every single time. For the approaching from the other side, so going from 1 to 0.5 to 0.1 to 0.01 to 0.001, we again see that the output we get every single time is 0, which maybe would lead us to believe then that the limit as x approaches 0 of sine of pi x, or pi over x, equals 0, right? Right? Maybe? Let's go to the graph again. So I'm going to go back to my calculator. I'm going to now graph the function y equals sine of, I should clear this out, sine of pi over x. Graph this, and we're trying to approach where x equals 0, so here near the origin. It's kind of hard to see what's going on, so I'm going to zoom in. And if you look right around 0, there's a lot of crazy stuff happening, right? So we see some points here on the graph where the outputs are 0. As we get closer and closer, there seems to be this crazy oscillation thing that happens. And if we zoom in even more, let's see. You can see it gets even more crazy. So it looks like the outputs are not really approaching any particular value because they oscillate so quickly. So this one, my friends, would be another one that is in fact not 0, but this would be one is where the limit does not exist. So we'll pull out our best Lindsay Lohan impression on that one. Hopefully a few of you know what I'm talking about there. All right, that's all I have for you guys for right now. Please remember to complete your classwork assignment before you do the homework, and let me know if you have any questions. Thanks for watching.